Hey, since there's no class Friday, we will try to I will try to make videos. Okay, so this video is basically trying to explain the some technical details about the last lecture. Uh, so just recall that previously we have proved that if you don't need any you only need one single two qubit unitary called a control knot plus all the single qubit unitary, then you already able to like generate any like unitary any n qubit unitary. So simply speaking, any 2 to the n times 2 to the n unitary you can decompose. You can write it as a product of either single qubit unitary or plus a two qubit gate control knot. Okay, but then we talk about this so-called discrete universal gate set such that the goal is to reduce this continuous single qubit to approximate by a product of finite ones. Okay, the idea is that right, so let me just talk about just recall idea. So idea basically you know that there's a thing called Euler angle, right? So Euler angle tell you that any unitary, if you forget about phase, you can write it as three different angles. The standard convention is YZY for some angle, but now we can do it by so the technical proof is that we can do it by just picking any two non-parallel axes, right? So you just take any m and any n, as long as they are non-parallel. Then if you have these two axes can be your rotational axis, and you pick the two-dimensional rotation, the SU2 rotation along these two, then you are able to construct any 2 by 2 matrices. Okay. So the standard so the technical result is that let's say we have this T called this is pi over 8 gate. So just quickly recall at the beginning that this. Okay, so this is pi over 8 gate. Right. So or you can write as 100 exponential I pi over 4. Okay. So this is called the T gate. And you have so this is recall this is the formula for single qubit rotation. Okay, so now let's say you have T and Hadamard, right? You have T and Hadamard gate. So notice that so now you need to use T and Hadamard to let you have two non-parallel axes, right? And this is possible because T represents one axis, let's say Z, and you have Hadamard, right? So Hadamard can get you the X axis, right? But technically, this is not a proof because we need some angle, right? We need that angle is irrational, irrational multiple of 2 pi, so that we can use the equidistribution theorem that we previously explained. So recall that this is the where is it? Okay, so this is the equidistribution theorem. Say that if you take an irrational number and take a multiple, integer multiple of this irrational number, then this irrational number can be arbitrarily close to especially any real number. Okay, so the idea is that so now we need to find a axis, right? Find two different axes. So the first axis, what we do is that we take exponential of minus I pi over z. This is basically T gate. And we can do this is x, but this x basically HTH, right? So I have T gate and the HTH, which I can generate by T and these two. Then I can compute this. Okay, so remember the formula. Formula says that exponential minus I theta dot with sorry. Let me do it again. So let me click. Okay. So remember that the formula looks like this, and with sigma. Sigma is a x, y, z. So n is a three-dimensional unit vector. Is cosine theta divided by 2 minus I sine theta divided by 2 and dot sigma. Okay, so it's very simple to remember it. So this is basically so theta is pi over 8, right? So it's cosine pi over 8 minus so sorry. So right, so this is right, so you can write as minus I pi over 8 and n just choose to be sorry. Is it there should be half here? Let me check. Should be half, right? Let me see the formula. Right, yeah, there's a half here. So let me see. So that means okay. So this is state. So this is formula. Okay. So now n is just 0, 0, 1, and right. So this is x, y, z. Right. So now this is theta divided by 2. Right. So you just plug. You just pick just whatever theta is. You just pick theta divided by 2, and then you find theta and then plug this formula. Right. So now this one is basically cosine theta pi over 8 minus I times sine pi over 8 times z, right? Because this is just z. And similarly, this is just cosine pi over 8 identity minus I sine pi over 8 x. Okay, so these are two rotation. And you just expand it, right? So you get cosine square pi over 8 minus I of cosine pi over 8 x and the z, and also z times x, right? So remember that y is ixc. Okay, so you can, after you do some combination, you get cosine square pi over 8 minus I of this guy times sine pi over 8. Okay, so now, this is rotation, right? Some weird rotation. Now, if now you can compare with this formula, this guy with this guy. Because I know that this must be a rotation, right? By definition, because the determinant is 1, right? So it must be a rotation. So I can compare this real. I can find axis of what this rotation means and combine and also find the rotation angle. Okay, so if we combine these two, what we get is cosine squared theta divided by 2 is cosine squared pi over 8, right? Because this should be cosine theta divided by 2. And then there's an angle here, right? So the angle, sorry, the axis information is in this bracket. This is n dot with sigma. So this is x, y, and z, right? So you can see the axis is the cosine pi over 8, and the z is a cosine pi over 8, and the y is sine pi over 8. Right, so you get some unnormalized vector, which is some weird axis, and then with some irrational multiple of 2 pi. Okay, so you find one axis and one weird angle. Okay, now you can use equidistribution theorem. Okay, so that means that any angle. Suppose I want to fix this weird axis and head, and doing the alpha angle, right? So alpha is very different from theta, right? Theta is here, so that means that I can do the I can do this weird rotation with this weird angle with multiple times, such that now this alpha is very close to alpha is very close to the multiple theta. And this using a wild equidistribution theorem. And simply speaking, that you just pick, yeah, you can just prove by Prince-Johann principle. Okay, so that means that simply speaking, when I use this n hat with some weird angle alpha, then I can use this n hat with some weird angle theta. I can use the multiple. I can just use integer times of this rotation such that these two are close enough. So this is equidistribution theorem. Okay, so in order to make it very concrete, we need to use some mathematical tool. Okay, so it's basically terminology. So discrete gate set cannot implement arbitrary unitaries, right? Because it's trivial, right? Because all the unitaries are uncountable, but if you have finite gate set and you make product of it, then the set is countable, right? So these two cannot be the same. But so we need to we can only do so-called approximate case. Okay, so I give you two unitary u and v. Then I can use this error measure. I pick all the states and which maximize this difference. Okay, so this is the error measure. Okay, so hopefully this is intuitive. Okay. Okay. So for why this is good, because that suppose I give you a POVN M, then this is the probability, right? The probability that I apply U to the state side. Okay. And the probability V is basically I apply V and I do the measurement. Okay. And there is a bound that one can prove that is PU minus PV is the total variable distance. Okay, you can check out the textbook proof. Their difference is 2EU U V. So this is the arrow. Okay, so the proof is basically using the idea of using a definition. So I will not prove. Let me just try to see how I can quickly maybe give the proof, or at least give you the idea of the proof. Right. So basically, you just need to try to bound this, right? But then you can use the previous formula. Just, let me see. So can I write as a U psi U digger? So this type of proof, I guess, most of using the finite difference, sorry, just the standard analytic techniques. Okay, so we can combine these two. So this will give you U minus V and this guy plus V psi, and this is psi U minus V take. Okay, so now you take trace M, but POVN is bounded by 1, so you can just bound it by this. Okay, and yeah, this sounds just some projector, right? So you can, I think this proves this. So you get two. You just get twice, right? Two times the error, right? Okay, so small ensures that small this error bounds ensures that similar measurement outcomes. Okay, and but if I write my U in terms of product small m gate U1 up to UM, so what this means that I approximate U by using the U1 up times up to UM and approximate V by V1 up to VM, then it's easy to prove that the total error of these two is bounded by the small pair error. So pair this, pair this, pair this. Okay, so the proof of this is very simple. We can just let me do n equals to 2, and then you can easily see the proof, see the general proof. So to prove n equals to 2, we just need to write everything down, right? So we want to compute U1, U2, U1 minus V2, V1, and we use a finite difference idea again. So we can write as U2, U1 minus U2 V1 plus U2 V1 minus V2 V1. So I can write as a U2 U1 minus V1 plus U2 V2 minus V2 and V1. So if I take any state here, then I can upper bound it, right? I take any state, I take any state. So this will less equal to the U2 norm times U1 minus V1 plus V1 norm, the U2 minus V2 and the V1 norm. So all these are norm. Okay, so but these are unitary, right? So it's norm is 1, right? So these are 1. So you get the 2 E of U1 V1. You get arrow bar with the arrow bound of U1 and V1 plus the arrow bound of U2 and V2. Right? So this is U2 and V2, U1 and V1. Right? So basically the idea is that you use the property of unitary, right? So that means that, okay, so if these are true, that means that if you want to have the measurement error tolerance, that means that each of small one, hopefully less or equal to delta divided by 2a. Okay, so since we have this tool, then by able distribution theorem, that means that if you give me epsilon, right, then I can find a multiple of weird angle rotation such that this Rn has multiple with n. Sorry, this n is different from n hat. This is the axis. This is the number of times the rotation, such that the difference is less than epsilon divided by 3. Right, so this is nice. So this means that I find a multiple of n such that it close to some weird angle alpha. Now I need another axis, right? But it's very simple. I just conjugate Hadamard with my original axis. I can compute this. Then you will get Rm alpha with m is the same as this. And the only difference is that y is there's an extra sign with y. Okay, and the reason is that I think I explained before because Hadamard conjugate with x is changed to z, and z is changed to x. But if you do y, there's an extra minus I sign, so you get minus I, minus y. So you just exchange x and z, and there's a minus sign on y. So you get minus y, and these two are already the same. So that means that if you give me any rotation along using axis m with weird arbitrary angle alpha, then I can do another n, which is such that the multiple of this n times with using axis m, they are close to epsilon divided by 3. Okay, and by Euler angle, that if you neglect about the phase, then arbitrary unitary can be using n, m, n, right? You guess it's similar as y, z, y, but now we're using two non-parallel axes. It's trivial that these two are, this m and n are non-parallel, right? You can prove by inner products. Okay, so that means that any unitary I can write as this way. So I can find a rotation r and alpha, sorry, theta with some power n, right? So m1, and for this m I can use rm n2, and for this one I can use r n n3, right? So that means that there any unitary u, there exists the three integer n1, n2, n3 such that this is the first big guy. This Hadamard conjugate is the second guy, and this is the third guy. So I approximately small u, small rotation, three small rotation by weird two rotations. Then I prove the results. Okay, so Hadamard and pi over a approximate any single cubic unitary to the accuracy apps. So this is the proof. Okay, and so for a multi-qubit circuit, right? So okay, so let me so these are just a summary. So we know that any M gate quantum circuit can so let's say it gives you M gate quantum circuit, right? Let's say using C9 single qubit unitary can be approximated by Hadamard C9T. Because the C9 is already the same, right? So I don't need to care. I only just expand all the single qubit unitary into Hadamard and T. So if I want the total circuit has circuit epsilon, right? So I use m of them, right? So for each of small one need, because the error will be additive. This is already proved. So each of small unitary, I need to do epsilon divided by m. If we use m gate, right? So the idea is that let's say you have the gate one, gate two, da 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 da. Now you approximate this guy by some another gate. Then if you want total difference to be epsilon, then each small one need to be epsilon divided by n, right? Because the error is it's additive, and the proof just using the chain inequality that we just explained before. So it's basically this. Okay. So we can summarize this section by asking so-called efficiency of quantum circuit approximation. So the idea is that how efficient is approximate quantum circuit with discrete gateset, right? So let's say, so this is an example. Suppose we know that approximate single qubit arbitrary two gates epsilon require 2 to the 1 over epsilon gates. So this is suppose. Then then for m gates, right? Then we need to remember that epsilon need to go to epsilon divided by m. So we get 2 to the m divided by epsilon, but each gate need to, but we have m of them, right? So there's extra m here. So we will need m times 2 to m divided by epsilon. So if this is true, then this is bad, because that means that the number of extra, the number of extra, the number of approximation is exponentially increase if we want m of them, right? Suppose I want to, so let's say m is polynomial, then we get exponential increase. Okay, but if you use the previous Eckert distribution theorem, then I think you can easily see that each single qubit gate you require 1/epsilon gates. The reason is that the proof is basically we discretize 0 to 2 pi angle with 1/epsilon well 1/epsilon we use yeah we discretize 0 to 2 pi using 1/epsilon different intervals. Okay, and then we use the equal distribution theorem. So by Pinch-Hall principle, there are only always two angles which fit into the single interval. So technically, you just need 1/epsilon gates. And by using this, then you just times m and 1/epsilon divided by m. So totally, if you use our previous method, then you get m squared divided by epsilon, which is quadratic increase. It's not that bad. It's not that bad. Okay, so there's a famous theorem called Solovay-Kitaev. The proof is very, you can check out Appendix 3, right? So all the unitary decomposition we use in this video or in this lecture are basically follow from Niels and Chung, chapter 3. Oh, sorry, chapter 4. So all these are like using the elementary method. But now if you know some Lie algebra, you can use some heavy mathematics. If you know some Lie algebra, then you can prove that single qubit unitary decomposed to epsilon to accuracy epsilon only using the log 2 of 1/epsilon gates. So this is exponentially better, right? Exponentially better than our 1/epsilon method because we use accuracy distribution. So now you get the log of it, right? So you can see this is exponential improvement. You can view that if epsilon is 1/2 to the n, then this would just require O of 2 to the n. So it's exponential, but for this one only take polynomial, right? So this is much more like sophisticated method. And so this implies that for m gates, then we just need this. Yeah. So this is polygrammatic increases over original circuit size m. So that means that if I give you a circuit size m, you just need to take an extra. It's almost the same as m, right? But only takes the polygrammatic increase. So this is very powerful. It just tell you that you just need a small overhead. And then this overhead is just polylog. Okay. So this is why this Solovay-Kitaev is a very deep results. And the proof is somehow like non-trivial. It's not so difficult if you know enough the algebra. Okay, so summary is that gateset, Hadamard phase, and C0 power of 8 are universal for quantum computation. So notice that this phase is not it's not important. It's basically T squared. Okay, so can simulate any circuit with C0 and arbitrary single qubit to accuracy epsilon. Okay. And the simulation overhead is polynomial in log m divided by epsilon if you know the Solovay-Kitaev theorem. Okay, so this is I should say the state of the art. Okay. So now finally we want to explain so-called approximate unitary gateset. This is similar as in a classical circuit, right? So in a classical circuit, if you're taking me n variable Boolean functions, then the number of functions is basically double exponential large. Say 2 to the 2 to the n, right? Because each of n bit string can either map to 0 or 1. So this is 2 to the 2 to the n. So this is very large. This is double exponential, right? It's not single exponential. And then Shannon proved that if you take some finite, let's say n or not, some finite universal classical circuit, then most of the function require exponential of them. Because if I give you the exponential number of finite gate, and then let's say m, then you can only use m of them, then you only get an exponential in terms of n, but the function is double exponential. So to match this to your n must be exponential also. And then this is true in quantum sense, right? So what we want to say is that can n qubit unitary U be approximate efficiently, right? For all U, right? So so previously we were saying that so now the problem is It's much more severe. We ask for general U. I give the element of this 2 to the n times 2 to the n matrices, and whether is this the easy way or the efficient way, or the number of the, or I can ask the number, what's the number of unitary, small unitaries that you can build to approximate arbitrary U. So the answer is that most of unitary require exponential many gates. So this is similar as a classical computation, the classical circuit theory. So let me explain the proof in detail. So we can ask if we start from all zero, then and I use m gates, and like one or two m gates. So let's say we have G gate types. So for example, Hadamard T pi over A, C naught, there are three, right? And each of acting on F at most F qubit. These G and F are fixed, some fixed number, right? So this is used very common in the lab because you can only take some finite gates, right? And some finite type. And there can only since they are finite, right? So F must be finite. Okay. So now suppose you have circuit, right? You have a circuit using total m gates. Now each of them, right? So now we don't need to count how many large unitary that then we can make. Right? So each of these guy, so each of these guy can take at most f different qubit inputs, right? So if I fix a gate type, then I can have n choose f different inputs, and there are g of them, right? Actually it's g here, right? But yeah, g here, right? So that means that n pick f, and I have g of them. G of them meaning that this guy, I have G choices because I have G gate type. So this is G. Okay. But we are sloppy, right? So I bounded this guy by n to the FG. So I move G to the exponential just for the convenience, right? So I make G to the exponential. So it's less equal to O of n of F times G. And there are M of them, right? There are M of them. So that means that this guy, so total you have n to the FGM. Right? Because you have m of them, right? So each one have n to the fg choices. Okay. So total you have total possible state that you can generate is n of is at most n to the power of gmf. Okay. Now suppose that right, because but all the problem is that circuit is uncountable, right? So we need to do some approximation. So the idea is that we use the previous error bound. So that means that we only count we identify two states. If they are the same, if their Euclidean difference is at most epsilon. So it means that we identify, let's say, psi 1 with psi 2 if their Euclidean difference is at most epsilon. Okay, so this is called epsilon-Ball method. Epsilon-Ball method. So we start with higher dimensional sphere, which is a quantum state, and then we patch this quantum state with ball with radius, let's say epsilon divided by 2. Yeah, okay. Or basically epsilon. Okay. So we want to match the sphere with state resolution epsilon. Okay. So let's say we need to just do some dimensional counting. Okay. So we cover n qubit state space. So notice that this space for n qubit states, right? Basically is in the dimension 2 to the n. But complex number, right? So you need to take it to be real. So 2 to n plus 1 minus 1. So minus 1 is the conservation, right? So conservation, or the normalization. So as a mathematical manifold, in terms of real manifold, its dimension is 2 to n plus 1 minus 1 sphere, right? Patch with radius epsilon. So maybe you see a plot here. So this is the ball and the issue patch with the sphere radius epsilon. Okay. So notice that this is just tell you that y this is 2 to the n plus 1 minus 1. Okay, and you can count how many sphere you need, right? It's very simple that you just count the number of volumes. Okay, so you first compute the surface, right? So this is the surface formula that you can find online. So basically, the dimensional D sphere with radius 1, the surface dimension of the surface area of d-dimensional sphere with radius 1 is equal to 2 to the pi divided 2 times pi of d over 2 divided by gamma d over 2. You can prove this by you can just find online find a proof online. So surface area is basically this, and you can also compute the volume. So you can compute the number of patches. And the computational is somehow like technically difficult, but the only thing you need to know is that basically it's this 1 over epsilon divided times 2 to the n plus 1 minus 1. Hopefully it's intuitive, right? So basically, but what is just tell you that the number of patches is exponential, is 1 over exponential increase. It's very large. Okay. So that means that state reachable with M gate is at most n to the MGF. Right, so you need this guy greater equal to this guy because this is all the state you have with epsilon resolution, and this is the state you can get with only using M gates. Right, so this tell me that this tell you that n to the FGM need to greater equal to 1 over epsilon to n minus sorry 2 to the n plus 1 minus 1. So this is if epsilon is 1 over m, or let's say if n of epsilon is 1 over m or something, right? Uh this is close to like n to the 2 to the n plus 1, which is double exponential, right? Because if you take a log, then you get a single exponential. Okay, so this guy is actually the same. It's a double exponential. If epsilon is 1 over n resolution. Let's say epsilon is constant at 0.5, right? It's still double exponential. So that means that you have a single exponential and you try to match it with the double exponential, right? So you can solve this m basically is okay. So let me just write it down. So you can just let's forget about you get this. And you just take a log. So you get mgf log n with basis 2. You get 1 over epsilon log 2 to the n. Yeah. Okay. So your m is omega of is at least 2 to the some exponential times log 1 over epsilon divided by log n. There are some fg here, but it's fine. It's basically some finite number. Okay, so that means that if epsilon is constant or whatever, this m must be exponential increase. Okay, so m is exponential increase. This is similar as the classical proof if you go back to the previous videos. Okay, so that means that exponential in n implies most unitaries are hard to approximate. And the best we have is this Solovay-Kitaev results that you give me n cubed unitary, we already know the answer must be exponential, right? So it's exponential 2 to the north. But you can see this is much better than this. I think so. If apps, right, you can I think one can check this. This is much better than this guy. Hmm? So this is fortunate. Okay, I mean so I will check this. But basically this just tell you that you need an exponential to approximate arbitrary unit. Okay, so universality construction is basically near optimal within polynomial factor. Okay, so yeah, so this is the summary of this quantum circuit model. Right, so in order to do quantum computation, you need to have you can arbitrarily collect your resources. You have some suitable space. You can allocate n qubit, and you can perform a state in a computational basis. You can perform a quantum, some elementary quantum gates, which we pick is here, or any single qubit plus C naught. Okay, and then perform measurement in a computational basis. So the problem for the rest of lectures to ask how powerful can this model compare to the classical one. Okay, so see you guys.